Continuing the first section on atoms and molecules and other little bitty things. 2 cells at home. I know a lot of times on a small screen you can't read these little captions, so I'm going to read them. And the lady cell is saying to the guy cell, "I'm talking to you. You're so thick membrane sometimes." The second class of molecules are what makes up those membranes. In case you were wondering what the heck this had to do with anything. Lipids are water repellent. They make a good water barrier. So a lining around a cell can really restrict what can go in and what can come out. And since every one of your cells is its own little dedicated bag of particular chemistry, you want it to not be completely at the mercy of what's around it or what's next to it. So you can have a muscle cell doing muscle cell stuff next to a nerve cell doing nerve cell stuff, next to a bone cell doing bone cell stuff. And lipids. Fats are made of lipids because they don't mix with water. The fats are pretty much a non-reactive form, and so it's a pretty good place if you're going to store some energy. It takes a little bit of energy to make them, but it's a really stable, non-mixing form of energy storage in us. We'll get to that on the list, because I'll make a list of this. Oils, vegetable oil, corn oil, canola oil, lipids, and actually a whole bunch of other things that will come up in our list of things that lipids do. Carbohydrates, not a heck of a lot of functions. Lipids, pretty decent number of functions. Lipids are waterproof barriers. Cell membranes. We've got a whole bunch of cell membranes piled up here. A lot of skin cells on top of other skin cells. And that makes us not lose water to the air very easily. We're fairly waterproof. That dates back to our distant fishy ancestors who moved from the oceans into the freshwater systems. And when you're surrounded by pure water, which is almost what freshwater is, and you are a watery environment, but not quite so much watery, you have to deal with the possibility of water flooding into your cells and popping them. So our fishy ancestors, one of their adaptations was to lipidize their scales and under their scales. And it's weird to think of, but the fishy ancestors that we have, what they call the bony fish, are waterproof. Even the ones that went back into the oceans afterward are waterproof. And that kind of set up our not so distant ancestors to take that protection from water flooding in, get into the air, and use the waterproof barrier to keep water from evaporating out. And the more dry the circumstances, the more waterproof animals and plants tend to be. Remember, waxes are a type of lipid, and waxy plants are an indication of the plant growing in a very dry environment, so it doesn't lose water in its leaves to the air very easily. As I said, cell membranes do a lot of other stuff. They have ways of letting stuff in, letting stuff out. That's because there's stuff stuck in the membranes that we'll talk about a little bit later. Not lipids, though. I already mentioned this one. So you're taking in a bunch of carbohydrates, and insulin comes out of your pancreas. Basically, your pancreas cells are tasting what's coming in from your digestive system. It's tasting for sugar. And as the sugar levels go up, your pancreas cells go, you don't want too much of this in circulation because your cells will use it. let's get this under control for a while. So it sends insulin out to your liver starts to store insulin. But your liver cells can get full. They can get full of the starches that you're storing it in. And when that happens, they just kind of let go of the insulin. It's okay, we can't respond to this, let it go. Out in your circulation, you have other insulin receptors on your muscles. They also store sugars as starches, but it's pretty much for their own use, is that because your muscles need a lot of energy. They'll take excess sugar in up to a point. And then, if the insulin is still in circulation, cells that are not that sensitive to it will start to react to it. Those are your fat cells. It's basically a way of saying to these cells, well, we tried to store the sugar every place we can store sugar, and it's all full. So would you take the energy in this sugar and make lipid molecules out of it? And that's what your fat cells do. They take the sugar energy that's holding the molecule together and use it to build lipid molecules, which are long strings of carbons that you can break down for energy later, the same way you open up a sugar and break that string of energy down. And as I mentioned before, because this doesn't mix with water, a big blob of fat in a fat cell might just as well be a little rock. It doesn't chemically react with anything, so it's a nice, safe storage medium. And when you need it later, you can break it down and use the energy from it. We're not that inclined to do that though, right? Is that once we got stuff stored in fat, we kind of leave it there as a last resort. So if you're continuing to eat carbohydrates and you're trying to work this stuff off, then your body's using the carbohydrates, unless you can exceed your energy needs by exercising, doing other kinds of things, or cutting your carbs way down. People that go on really low carb diets, they will exhaust the stored carbs they have in their liver and in their muscles, and then it's like, well, we got to go get energy from somewhere, and it'll go after the energy stored in your lipids and in your proteins too. Now, some people that's bad for is that some people, when you break lipids down for energy, you break proteins down for energy, it releases fatty acids and amino acids, and it can actually acidify your blood to the point where your blood isn't interacting with your cells right. It's a rare side effect of a no carbohydrate diet, but it does affect some people, and it can be pretty dangerous in a very rare subset of people. So if you're going to go on a low carb diet, got to watch out for some stuff, or no carb diet. Anyway, long-term energy storage. Put it there, get it back later. In us, this is not a big deal for heat. We are still essentially tropical animals. Our ancestors evolved in the plains of Africa, right on the equator. So we evolved in pretty warm circumstances. And when we moved away into cooler circumstances, we didn't really physically adapt so much as we changed our immediate environment by building houses around us and putting clothes on. So heat insulation is not that big a deal in terms of lipids in people, but padding insulation is that we do have places where we use insulation to protect some of our organs, and even then, not a lot. Is that when we dissect the pigs later in the semester, when you open up the scrotum in a male, is that the testis has a lot of fat around it, and that is a not terribly effective impact pad. We'll talk later about the weirdness of why the sperm production machinery is outside of the body, where it's pretty vulnerable to injury. The best we can do is pad it up a little bit. There is, while I'm thinking of it though, around your eyes, between your eyeball and your eye sockets, there are pads of fat, so that if you move your eyes quickly or you get hit in the head, that eyeball doesn't smack into the bone. It hits the pillow between the eyeball and the bone, and that absorbs a lot of the impact. So there are places that we use padding insulation other than around testicles. Here's a really big one. we make hormones out of two different types of molecules. Lipids, and the next one that's gonna be on the list, proteins. Is that lipids are a little tricky, they don't dissolve in water real well. In fact, when we digest lipids, we have to have them carried around in our blood to get them to dissolve at all, and they don't really dissolve that well. We'll talk about that later when we talk about the carriers. But in some cases, we need a hormone that can come up to a cell and go right in and do what it needs to do. And so we make hormones out of the same material we make cell membranes out of. So the cell membrane is a much smaller barrier to steroid hormones. And a lot of these are based on cholesterol, that's what the steroid comes from, and they have stero in their name, like progesterone and estrogen and testosterone. Not all steroid hormones are named that way, but an awful lot of them are. And they just have an easier entry to the cells that they're gonna have effects on than the protein-based hormones that basically have to come up and ask nicely by interacting with molecules on the surface of the cell. Okay, that's lipids. That makes for a very short entry. And we'll stop here.